Hello everyone. Sorry for there's some noise coming from outside. Some people are unpacking stuff, but I hope you were able to hear me. My name is Adriano Koshiyama. I'm here to introduce you the Machine Learning Institute certificate. On behalf of the MLI faculty, I wish you all welcome, and we would love to have you in the course, and we would like to have this course as much enjoyable and fruitful and educational as possible. So we encourage feedback, we encourage interruptions. We want to hear you more. And I think going forward, I think you probably would really enjoy the whole course and the modules, how we have structured themselves and so on. So really happy to have you in, and you can use the chat. I guess it's working, the chat, so maybe in the end I can answer some questions, but you can just formulate them and then I can go back and forward in the slides, so it's no rush. Okay, so I'm just going to go forward. So this is certificates, and let me just pass the slides. Next slide. Number 2. Oops, I always forgot. Page down. Yeah. Yeah, find it. Yep. Page up, page down. Nope. Oh, wait. Yeah, so you need to get me clearance first. Yeah. Now it's good. Yeah. It was clear for me. There was something wrong happening here. So we've done this before. So okay. So this is slide deck. So I'm going to present you the MLI timeline. What do you learn, your materials, some prerequisites, always important, and the Q&A session to finish. So what's the timeline? So the course starts with some Python for data science and artificial intelligence. And question, I think nowadays it's less problematic to explain why we're going to use Python. I think everybody pretty much have got some feedback or have read some stuff or have seen your collaborators and friends and boss and potentially or employees using Python in some respect. So I think everybody knows the importance of Python. Back in the old days, we would always have to justify why you're using Python and not R or MATLAB, but I think it's clear. And there was a very recent report from an IEEE, basically a mass survey about which programming languages are being used more in industry, and Python is basically topping the polls, followed by Java, which is very impressive, very impressive. Like first time Java is being beaten by another language. That's very impressive. So we start with the Python for data science and artificial intelligence. So you learn how to code and at least get up and running so you can understand the rest of the course. First module is a module that I teach, which is supervised machine learning. It's one of the basic learning paradigms of machine learning. It's pretty much the most successful one. So most of the tools you see being used by Google, Facebook, or Amazon, I mean in terms of image recognition or natural language processing and so on, they're all supervised machine learning tools. And I would say, if you know really well supervised learning, you're probably going to do really well moving forward, because you got the basic and you got what actually is working, has more evidence about it. Second module is unsupervised machine learning, where I think it's Ivan probably going to teach it, and you learn clustering and dimensionality reduction and other techniques. It's very important, and these two learning paradigms, supervised and unsupervised, they also feed into each other. So they're not completely separate apart, and you can use one to help another. Then module 3 is practitioner approach. So you're going to learn the arts of data science, not the theory of data science, but the art, or how you do stuff, how do you proceed in real life. Um, I think things are very different when you have to sit down and code and wrangle with real data compared to toy problems and other stuff that we get in textbooks. And I think this module fills this gap. Module 4 will be particularly focused on neural nets, and neural nets because, well, we are in the neural nets age. A decade ago, we were in the beginning of the neural nets age, but more in the SVM age. 2 decades ago, we were in the random forest or ensemble age. So now we are in neural nets age. So it's good for you to know what a neural net is, how do you train one, how do you test one, what are the main variations of neural nets. And module 5 basically goes to the state of art, which is what we call deep learning. That is basically pushing neural nets to the extreme. But not only neural nets, there are other models. They are not necessarily neural nets, but they are also part of deep learning as a learning paradigm. So, and reinforcement learning, which is the less applicable in practice, but I guess going forward is the most interesting learning paradigm of all of the 3: unsupervised, supervised, and reinforcement. Reinforcement is the one which I think most of the robots and autonomous vehicles and so on will be tapping into. Module 6 is time series, which is very important. I guess we are in finance, and most of the data we have in finance are time series. So that's a very key module, so you can use all the knowledge you have harnessed before, and you see that you need to make some small tweaks in the algos, but in general, you're pretty much covered. Final project and submission and final examination. So that's the timeline. So starting with module 1, you will learn a lot of algos. So you will learn ridge and lasso regression, which are variations or maybe generalizations of linear regression. They are very useful when you want to do feature selection on the fly. Ridge and lasso are great tools for that. Classification regression trees, great models for explainability by design, which is a very topical in this moment. Gradient boosting trees and random forests are ensemble-based approaches. So that's 90s, but people still use to this day. And random forest is particularly a lot used in the industry. And then 3 other approaches from the last decades, which are the kernel methods. So you have kernel ridge regression, linear SVM, and kernel SVM. And you also learn a few others, but these are the basics. And then with these basics, you're covering around 70% of the different methodologies to model in supervised learning. You have linear models, you have piecewise linear models, you've got ensemble models, kernel methods, and neural nets. But neural nets is a module ahead, which is not covered here. But if you learn neural nets, that will be basically covering all the possible models available in supervised machine learning. And practical examples that you can do with supervised learning, you can predict your events, you can do proper machine learning, model fine-tuning and validation, you can build trade recommendation systems, you can do all sorts of things, and it's very useful, and particularly if you're doing sentiment analysis or if you're doing forecasting, what you're doing is supervised learning. That's what the basics. Next module is unsupervised learning, and as I said, you will learn dimensionality reduction techniques like PCA, which I think a lot of you may be aware of, autoencoders, which is a neural net approach for dimensionality reduction. Yeah, you can call it a neural net approach for dimensionality reduction, which is another way. doing. It's a bit more nonlinear instead of just doing linear projections. You learn cluster analysis like k-means, db-scan, hierarchical clustering. These are techniques to cluster data. So in dimensionality reduction, what you're doing is basically reducing the number of features you have. So you have 100 features, then you can reduce that to 4, 5, 10. So you're reducing the columns of your spreadsheet. In clustering analysis, what you're doing is reducing the rows of your spreadsheet. So you're acting on both directions when you have both. You learn some other techniques which are not easily classified as supervised learning. They are probably more unsupervised, and that's why they're here. Outlier detection using global KNN, and some generative algos. I think Ivan wants to teach you about GANs, but you can also have VAEs and some other techniques. Generative algos are very useful for when you want to replicate some data sets. So if you have a bunch of assets and you want to create a synthetic version of them for backtesting, that's very useful, and maybe he's going to have a paper about it, so it's probably maybe end up showing this. And it's basically you have an asset and then you build a GAN for that. A GAN is a generative adversarial network, and using this GAN you can create synthetic versions of the assets. So you build your trading strategy in the synthetic samples, and then you test the trading strategy in the actual observations. So you never backtest over fits because you're not usually using the actual data. That's a good way to avoid that. Practical examples, you can do customer segmentation. You can do NLP for article summary and block classification, stock segmentation. And I think the most classical one, you can do bond yield curve dimensionality reduction. People usually do this via PCA, and there's a good interpretation. When you do PCA on a yield curve, every component of the PCA has a meaning, like the level, the trend, slope, and some other components. But if you use autoencoder, you end up with some different meanings, and maybe it's a little bit better if you want to build a strategy on that. So the practitioner approach, you will delve into more details. In supervised learning, I cover some of that, like cross-validation, regularization, model performance evaluation, etc. But I cover them quite quickly because that's not my topic, because I know that later on the practitioner approach will delve into that. And these 4 components, cross-validation, regularization, evaluation, and feature engineering, they are very key, because without them, you don't know if your strategy works or not work, if your model is not doing well or not. You don't know what's the worst case that your model will perform. You end up overfitting, and you don't know how to deal with overfitting, or your model simply, you don't have enough signal on your data, but maybe you can manufacture signal, and doing feature engineering is a way for you to manufacture that. Or you have a lot of features. Some of them maybe are spurious correlated with the thing that you're trying to predict. And if you know how to do feature selection properly, you are able to avoid them. So that's very important in practice. In theory, when you do supervised learning, you kind of don't care much about that. You're caring more about the models and what they do and so on. This is really much, okay, here's the data set, and here's the model. How can I make this relationship work better? That's why this particular module. And there are some practical examples that you can do that, like bond price forecasting using NLP, market impact assessment, diabetes classification. You can do all sorts of things using these 4 techniques. And these 4 techniques, they are not only for machine learning, but they also can be used to improve some statistical modeling or any other technique you're using, particularly cross-validation, which is It's a methodology that, was devised a long time ago, goes back to René Descartes and so on. And we kind of forgot about that, particularly in the stats course. We are just very much focusing on R square and things like that. And cross-validation is another way for you to assess models. And in my view, and not only my view, but in theory as well, you are able to compute the average generalization performance of your tool. That's very, very important when you want to deploy something in real life. Another module, and I think they put this together, is deep learning module. And deep learning with reinforcement learning, but also there's a neural network module. And you will learn about dynamic programming, Monte Carlo methods, TD methods, like temporal difference methods, like SARSA-Q-learn, DPQ-learn. And these techniques, they are, I guess, in financial markets, the clear application for them is in algorithmic trading, because that's where you have a clear sequence and a lot of feedbacks coming, and you need to react to them. And you don't have a model for the system, so you need to learn the model of the system as well. So you have all this very interesting situation. And as I said, going forward, this seems to me the most the winning paradigm. We're still in the supervised learning because we've got so much data, and we still can mine that data. But going forward, I feel that we are going to focus more in the reinforcement learning. And you can use that for optimal market making. Some people use that for hedging. There's a deep hedge paper, which is very interesting. You can use that to play optimally blackjack. You can use that to win, as Google DeepMind did, to win the game of Go. You can use that for that. Or you can use, as Google did as well, for StarCraft. You can use it for many problems. But I guess in finance, algorithmic trading might be the most interesting application for reinforcement learning. And neural nets, you will learn, I think, the basics, particularly backpropagation. Backpropagation is it's a very simple technique. It looks kind of magical, and people have come up with so many blogs and tutorials about what is backpropagation, but it's basically a chain rule, but also with this idea that there is some kind of hierarchy where the errors will spread across a network. And even though you're going to learn this in a very tedious way, you have to understand that nowadays, because of PyTorch and TensorFlow and all these frameworks, they do this for you in the background. And they do this in a very smart way, using this thing called computational graph, which is this kind of global register about where the data is flowing, what are the relationship between one node of the network with the others, and now what actually the operations are happening. So what are you doing? Are you just multiplying this by a number, summing another number, squaring something? And if you're able to decompose this in very basic operations, like the ones I said, the derivatives are calculus 1. You don't need to know anything about derivatives of exponentials or very complicated ones, or sines and cosines and hyperbolic tangents and things like that. You don't need that. You just need to know very basic derivatives and know the chain rule and know how to accumulate the whole chain rule. And that's why we need the GPUs, because the GPUs will do the whole calculation of the chain rule for you instantly, instead of having to do via CPU in a serial way. That's very important. So you learn backpropagation, the perceptron model, which is the foundational model in neural nets. Perceptron model is some of you see in the classifications a bit strange, but if you use perceptron for regression, you see that's basically linear regression with some nonlinearity. That's what you're doing. You learn some optimization techniques like gradient descent. That's how we train most of the neural nets back in the old days. Nowadays, we train most of them using SGD, which means stochastic gradient descent. That's why, in a way, another explanation of why neural nets have won the war against SVM and random forests was because they are more scalable. So you can train neural nets with whatever amount of samples, and they scale really well because you're not evaluating the architecture, the parameters using old data. You're always taking small batches of data. So regardless of the size of the data set, I'm always observing batches, and this really make the whole training process very quick and very scalable. And you can even go to the level of just give me one sample at a time, and I can update the neural net. And you learn a lot of architectures, and I guess feed-forward is the classical one. It's basically a generalization of perceptron. You learn RNN, which is a recurrent neural network. But I guess most importantly, you learn LSTMs. LSTMs are long short-term memory. They are very nice networks. They are very useful to model sequences, and you can model sequence of text or movie or time series. So everything that is a sequence, you can model via LSTM, and they are providing most of the state-of-art results, beating up ARIMA and some other models by a large margin. And if you're playing with images, you can do CNNs. CNNs are convolutional neural networks. They are very, very useful for images, and they are basically the pillar of most of the successful applications and deployments of image recognition in practice. So I think we're kind of, maybe not, but I feel that we're pretty much getting some basic or building blocks on how we solve problems in general using neural nets. So if you have an image problem, an image recognition problem, you can use CNNs. If you have a sequence, you can use LSTMs. If you have nothing in between, you can just feed forward. That seems to be getting, I guess, more emphasis and more results and evidence. And I guess the community, in a way, is getting to this consensus about how do you solve different problems using different models. And using that, you can solve time series forecasting, image classification, natural language processing, and so on. It's really incredible, and I think, I guess the last point about neural nets, and going back to the prediction error approach, is that neural nets manufacture for you features. So it kind of solves you one of the big problems we have is always about thinking about how can we create features. And one of the fundamental principles about neural nets that the neurons, they are features. So you are manufacturing them on a data-driven way. So that's another plus of neural nets. So your materials, so every class, you get lecture notes, which is basically the slides, sometimes some real proper lecture notes, video records. So every class is recorded, so you get a video copy of that. You get Jupyter notebooks. Jupyter notebooks, maybe some of you know, maybe some of you will get to know. It's basically a file that is usually written using Python. And it's quite a nice thing because you can open the browser and it's very interactive, so you can write codes and you can get the output in front of you. So in a way it looks like R, but it's a little bit more organized because you have a sequence. So it's like a notebook really. and you can put markdown text too. So if you want to report something that makes code and texts and equations and things like that, Jupyter Notebook is becoming kind of the standard. It becomes so much standard that there's something called Colab, Google Colab, which is a collaboratory version of Jupyter Notebook, and that's very useful for teaching because people can just make a Google Colab notebook and put it online, and people can access it from anywhere, even though their computer might not be very good, because in the back end, when you open a Google Colab, Google is giving you an infrastructure. So Google provides you with some memory, Google provides you with some CPU, and also, most cases, they also provide you with a GPU, which is very important if you're doing neural nets. Data sets and some prerequisite materials. That's the material you're going to get when you, by the end of each class. I guess most of the prerequisites when you're doing machine learning is linear algebra. The mathematicians would say machine learning is a glorified version of linear algebra, which might be true in some respect, but sometimes I think it's not only linear algebra, it's also optimization, it's also probability theory and statistics, so it's everything in between. And I think if it was just that, we would be in a statistical modeling course, right? Statistical modeling course would be linear algebra, maybe some optimization because of maximum likelihoods, probability statistics. And the only thing that differs a lot machine learning from a statistical modeling course is the computational element. So in machine learning, you are way more focused on delivering value, solving a problem, using algos to do that. In statistical modeling, you are very concerned about the model, the assumptions, what's going on, and so on. So you're kind of very model-centric. In machine learning, you are problem-centric, and you want to solve the problem regardless of the model you're using. So it's a little bit of a shift in terms of mentality, and maybe that's why it's becoming a little bit more successful, because you're focusing on the right thing. But who knows? In the future, you can always go back, right? So these are the prerequisites for the whole MLI course. Some of that will be built over time. So not necessarily you need to be on an intermediary level. If you have just a basic understanding, you can get to know some of them, and you can always ask the teachers for materials. So I'm gonna close it now, and I'm gonna look for some quick Q&As. So if you have any questions in the chat, you can just message me now, or if you have any questions over here too, we can have a conversation about it. But that's it from my side. Thank you very much. Okay. There's a question here in the chat. You guys, no questions?
Do you have a platform, your own platform that starts with Adriano, or is it like for deploy?
You mean
Like
for
the notebooks?
the notebooks could be also locally deployed, because they're going to give you the notebooks. I guess if we put the notebooks in Google Colab, then we'll be using Google backend to run stuff. But I suppose most of the stuff will be running on your machine. We're not going to, I guess in my course, we're not going to do things very heavy.
Okay.
But I guess in the neural nets course, it would be good if you have a GPU.
I mean, there are like, do you consider like the examples of people work with, like they review and all, right? And I guess the workload is the other question, right?
Yeah.
But I mean, it's like the example of the program not going to be very
Yeah, yeah.
And yeah, and then so forth, and kind of help.
Absolutely, yeah. I feel, for instance, if you're doing a neural nets course, I suppose if you have a GPU in your computer, your life will be probably easier. But you don't need a GPU to run it. You can do via CPU as well. It may take a little bit more time, but that's okay. That's okay. I guess that's it. Well, thank you very much. It was a pleasure, and I see you soon, I suppose. Bye bye.